storm is moving through space, but it will not look like a storm at first. No clouds, no thunder, just a magnetic cloud leaving the sun, crossing 93 million miles and quietly aiming at the systems that keep modern life running. Power grids, satellites, GPS, polar flights, radio signals, even the northern sky could all react within the same narrow window. The official forecast calls it strong, not extreme, but one hidden measurement could still change everything. So what happens if the magnetic field turns south? Which continent feels it first? And what fails before anyone notices? The watch issued before the shock arrived. The first warning did not sound like an alarm. It appeared as a block of operational text, written in the plain language of forecasters who watch instruments before the public sees anything in the sky. The office was not on a mountain or beside a telescope. It was in Boulder, Colorado, at the Space Weather Prediction Center, where the weather being measured does not form in clouds. It begins 93 million miles away, in magnetic disorder on the face of the sun. At 22:11 UTC on June 6, 2026, NOAA issued a geomagnetic storm watch. The predicted higher storm level was G3 for June 8th, followed by G2 for June 9th. A G3 storm is classified as strong. It is not the language used for a civilization-ending event, and it is not the language used for a routine aurora forecast. It sits in the middle category where the sky becomes visible, satellites require attention, radio users notice gaps, and power grid engineers start looking for currents that do not belong. The source was a coronal mass ejection that left the sun on June 6th. In the forecast discussion issued the following day, SWPC described the solar trigger. A moderate M-class flare from region 4461 occurred at 14:01 UTC. It produced a 10.7 centimeter radio burst, an 11-degree-long filament eruption near the southern solar hemisphere, and a Type 2 radio sweep with an estimated speed of 838 kilometers per second. The resulting partial halo CME was first seen in LASCO C2 imagery at 14:01 UTC, and NOAA expected its shock to arrive around midday on June 8th. Hold that thought, because partial halo is the first clue that this is not just a bright flash, it is geometry. A halo CME is what an eruption looks like when solar material expands around the sun from Earth's point of view. It can mean the eruption is coming toward us, moving away or spreading wide enough that direction is difficult to judge from one line of sight. A partial halo is less complete but still important. It means the ejecta was broad enough in coronagraph imagery to wrap across a significant portion of the solar disk. The event does not need to be perfectly centered. It only needs to place enough magnetized plasma between the sun and Earth. Between the sun and Earth, there is no empty road. There is the solar wind, already flowing outward at hundreds of kilometers per second. There are magnetic fields embedded inside it. There are streams from coronal holes. Old disturbances from earlier eruptions weaken as they move, but still shape the medium the next eruption must cross. NOAA noted that solar wind conditions were waning after earlier CME and possible coronal hole high-speed stream influences. The background was a disturbed system relaxing just before another disturbance arrived. The forecast numbers were specific. For June 8th, NOAA's 3-day forecast expected the planetary K-index to reach 7 between 18L and 21D UTC, the threshold for G3 storm conditions. Earlier intervals carried G1 and G2 values. June 9th was forecast to begin with G2, then fade through G1 and below storm levels. The structure shows the event as a sequence, not a single impact. First comes the shock, then comes the compressed magnetic field, then comes the question that forecasters cannot fully answer until spacecraft upstream of Earth measure the direction of the interplanetary magnetic field. The question is B's. If the magnetic field inside the CME points northward, it resists coupling with Earth's magnetic field. The storm can underperform. If it points southward, it connects more efficiently, opening a pathway for energy to pour into the magnetosphere. That is why space weather forecasts carry uncertainty, even when the CME is already visible. Forecasters can estimate speed, width, and arrival time. But the magnetic orientation that decides intensity is often not confirmed until the disturbance reaches satellites near the L1 point, about 1.5 million kilometers upstream from Earth. That becomes important when the phrase power grid enters the story. A geomagnetic storm does not attack a power grid the way lightning hits a transformer. it changes the magnetic environment around the planet. When Earth's magnetic field fluctuates, electric fields are induced at the surface. Those fields can drive geomagnetically induced currents through long conductors, transmission lines, pipelines, rail systems, undersea cables. The current is slow, almost direct current-like. Large transformers are built for alternating current. Add a slow current through their windings, and parts of the magnetic core can saturate. Heat rises, reactive power demand changes. Protective relays may see conditions that look like faults. NOAA's scale is careful about this. At G3, power systems may require voltage corrections, and false alarms may be triggered on some protection devices. At G2, high-latitude systems may experience voltage alarms. At G5, the extreme category, widespread voltage control problems and even blackouts become possible. This watch is not a G5 watch. That distinction matters, but dismissing a G3 event as harmless also misses the point. Modern grids are continental networks, loaded differently by hour, weather, market demand, and maintenance schedules. A storm that is manageable in one grid state can become more complicated in another. The three-continent part is geographic. The auroral oval and the strongest induced current risk favour high geomagnetic latitudes. On the night side of Earth, that ring passes over northern North America, northern Europe, and northern Asia. Canada and the northern United States watch the same storm that Scandinavia watches several hours later, and Russia's high-latitude transmission corridors sit under the same planetary disturbance as the oval rotates with Earth. The storm is global, but the impacts are local. Ground conductivity, grid length, transformer design, and operator preparation determine what actually happens. There is precedent behind the caution. In March 1989, a severe geomagnetic storm collapsed the Hydro-Quebec grid in about 90 seconds, leaving millions without power for hours. That event was far stronger than a routine G3 watch, but it remains the modern case study because it showed how a disturbance in space can become a failure on the ground. To grid operators, it became a permanent lesson. The sun does not need wires to enter the power system. This event begins before the storm arrives. It begins with text issued from Boulder, a partial halo captured by coronagraphs, a radio sweep moving through the solar corona, and a forecast that places the strongest interval on June 8th. The next 72 hours are not a countdown to guaranteed failure. They are a test of timing, magnetic orientation, infrastructure, and interpretation. The event is coming through the high-activity years of Solar Cycle 25, whose maximum period NASA and NOAA announced in 2024. What happens next depends on a magnetic direction that has not yet crossed the spacecraft at L1. The magnetic cloud between the Sun and Earth. Between the Sun and Earth, the disturbance does not travel like light. A coronal mass ejection takes much longer. It carries ionized gas and frozen-in magnetic fields through interplanetary space. It moves as a structure, not a flash. It has a front edge, a compressed sheath, a magnetic interior, and behind it, a wake where the ordinary solar wind tries to settle back into place. The June 6th eruption began with an M1.8 flare from region 44661 at 1401 UTC, according to NOAA's forecast discussion. That active region sat near S21 East 12, slightly south of the solar equator and east of the central meridian from Earth's point of view. The event produced a 10.7 centimeter radio burst, an 11-degree long filament eruption centered near S25 E28, and a Type 2 radio sweep with an estimated speed of 838 km per second. The resulting partial halo CME first appeared in LASCO C2 coronagraph imagery at 1401 UTC, with arrival expected around midday on June 8th. That detail matters because it suggests an Earth-directed component, but not cleanly enough to remove uncertainty. A coronagraph blocks the bright disk of the Sun so faint material around it becomes visible. The Sun is hidden behind an artificial eclipse. Around the occulting disk, the corona appears as pale streamers, rays, and magnetic loops. When a CME leaves, the quiet geometry bulges outward. A white front lifts from the solar limb. If it spreads around the disk, forecasters ask whether the eruption is moving toward Earth, moving away, or expanding so widely that it only appears threatening from one line of sight. The partial halo seen on June 6th gave direction, width, and timing. It did not give the most important parameter. Hidden inside the ejector is a magnetic field that can point north, south, or rotate as the cloud passes over Earth. That north-south component is known as BES. In operational space weather, BES decides how efficiently the CME can connect with Earth's magnetic field. Northward BES tends to reduce coupling. Southward BES couples more strongly with Earth's dayside field, allowing more energy to enter the magnetosphere. The problem is that BES cannot be reliably read from a chronograph image alone. The image can show mass and speed. It can show whether the cloud appears wide, narrow, asymmetric, or Earth-directed. It can justify a watch. But it cannot fully reveal how the magnetic rope is twisted inside the cloud by the time it reaches 1 astronomical unit. Over 2 days, the CME expands, rotates, interacts with background solar wind, and sometimes merges with older disturbances. The structure leaving the Sun is not always the structure that reaches Earth. This is where the Deep Space Sentinels become important. NOAA's DS-SCOVA spacecraft sits near the Sun-Earth L1 point, roughly 1 million miles from Earth. NASA describes SCOVA as a space weather station that monitors the solar wind and provides alerts and forecasts for geomagnetic storms that could affect power grids, satellites, telecommunications, aviation, and GPS. NOAA explains that the solar wind reaches L1 before it reaches Earth, usually giving 15 to 60 minutes of warning before a CME's particles and magnetic field arrive. Picture the arrangement in space. Earth is moving around the Sun, the Moon is moving around Earth. Far upstream, nearly between the planet and the star, DSCOVA holds position in a gravitational balance point. It follows a looping orbit around L1, watching the flow coming from the Sun. Its instruments measure solar wind speed, density, temperature, and magnetic field. Those values arrive as graphs before they become public warnings. A jump in density suggests the shock has arrived. A surge in speed confirms the front is passing. A rise in total magnetic field shows compression. Then everyone watches BES NOAA's June 7th forecast describe the background before arrival. Solar wind parameters reflected waning CME and possible weak positive polarity coronal hole high-speed stream influences. The total magnetic field ranged from 3 to 5 nanotesla. BES was mostly benign, with no significant southward deflections. Solar wind speeds gradually declined below 550 km per second. In other words, the system was relaxing before the next impact. NOAA then expected a disturbed solar wind environment to return by early to mid-UTC day on June 8th, with shock arrival bringing enhanced magnetic field and faster solar wind, continuing into June 9th before beginning to wane. That is the sequence hidden inside the warning. The shock arrives first. It is the pressure wave driven ahead of the CME as it pushes through the solar wind. Behind it comes the sheath, a turbulent region where plasma and magnetic field are compressed. The sheath can be geo-effective on its own if BES turns strongly southward. After the sheath comes the ejector itself, often smoother and more organised than the material ahead of it. Some storms peak in the sheath, others wait until the magnetic cloud arrives and the field turns south for several hours. That is why NOAA's 3-day forecast reads like a staged escalation. The greatest expected 3-hour KP East for June 7th through June 9th is 7, the threshold for G3. On June 8th, values are forecast to rise from unsettled conditions into G1 by 12 hours to 15 UTC, G2 by 15 here to 18 UTC, G3 by 18 to 21 UTC, then G2 from 21 to 0 UTC. June 9th begins with G2, then steps down through G1 and below storm levels. The probability table issued June 6th showed a 51% chance of strong to extreme storm levels on June 8th and 25% on June 9th. It is a window, not a moment. The wider context is Solar Cycle 25. NASA and NOAA announced in October 2024 that the Sun had reached its solar maximum period, the phase when sunspots and eruptions become more frequent. Solar maximum does not mean every event is extreme, it means the background probability rises. More active regions cross the Earth-facing disk, more magnetic fields twist, shear, and reconnect. More eruptions enter the forecast pipeline, and more days begin with routine-sounding text that can become operationally important by nightfall. By the time the June 6th CME reaches the last million miles, the forecast will depend on measurements that were impossible to know with certainty at launch. But the final test belongs to the magnetic field passing over L1, where a small spacecraft reads the storm before Earth feels it. If BES turns south and stays there, the watch becomes a storm. If it turns north, the event may arrive with less force than the imagery suggested. The power grid question begins in that narrow strip of space, where a magnetic cloud crosses a machine built to notice the invisible, the grid that feels the sky. A power grid does not look vulnerable from the ground. It looks heavy, engineered, and fixed. Steel towers rise out of fields, substations sit behind fences with gravel yards, warning signs, porcelain insulators, and transformers the size of small rooms. Transmission corridors cut through forests and over hills in straight, deliberate lines. The equipment is built to survive lightning, wind, ice, salt, heat, and decades of ordinary electrical stress. But a geomagnetic storm does not enter through the same door as ordinary weather. It begins above the atmosphere, where the solar wind transfers energy into Earth's magnetic environment. NOAA describes a geomagnetic storm as a major disturbance of the magnetosphere, produced when energy from the solar wind efficiently enters the space around Earth. The strongest coupling happens when the solar wind carries a sustained southward magnetic field, opposite the direction of Earth's dayside field. That southward orientation allows magnetic reconnection, and reconnection is the mechanism that turns a moving solar cloud into a planetary electrical disturbance. From space, the system looks elegant. Earth is wrapped in a magnetic shield. On the sunward side, that shield is compressed by the solar wind. On the night side, it stretches into a long magnetotail. During a storm, currents intensify in the magnetosphere and ionosphere. Some follow magnetic field lines toward the polar regions. Others form auroral electrojets, fast-flowing current systems high above the surface. The sky may respond with green curtains and red arcs. The ground responds differently. It feels the changing magnetic field as an induced electric field. That detail matters. The current that threatens a grid is not thrown down from the sky like a bolt. It is induced in the Earth itself. When ionospheric currents change rapidly during a geomagnetic storm, the changing magnetic field induces electric fields at the surface. Those electric fields drive geomagnetically induced currents, or GICs, through any long conducting path available. The British Geological Survey describes the paths plainly: high-tension electricity transmission lines, oil and gas pipelines, and transformer groundings. The reason power grids are exposed is length. A short wire does not collect much induced voltage. A transmission line hundreds of kilometers long can. The longer the conductor, the more ground potential difference it spans. The current enters through grounded transformer neutrals, moves through the windings, travels along the line, and exits through another grounded point. To the grid operator, it can look like a slow, unwanted current riding underneath the normal alternating current system. Transformers are the central concern because they are not designed to carry direct current through their magnetic cores. A geomagnetically induced current behaves almost like direct current, compared with the alternating current of the grid. It pushes the transformer core toward half-cycle saturation. Once saturation begins, the transformer no longer behaves cleanly. It draws reactive power, it produces harmonics, it heats unevenly. Protective relays can misread the conditions. Voltage control becomes harder. The system remains standing, but it becomes less forgiving. NOAA's own space weather scale places that risk in operational terms. At G2, high-latitude power systems may experience voltage alarms, and long-duration storms may cause transformer damage. At G3, voltage corrections may be required, and false alarms may be triggered on some protection devices. At G4, widespread voltage control problems become possible, and some protective systems may mistakenly trip key grid assets. At G5, the scale includes possible grid collapse, blackouts, and transformer damage. The forecast watch for June 8th is G3, not G5, but the difference between those categories is exactly why grid operators track the storm before it peaks. In a control room, the storm is not visible as aurora. It appears as numbers changing on screens. Voltage begins to wander, reactive power margins tighten, transformers report neutral current. Operators may shift generation, adjust voltage support equipment, delay maintenance, or take assets out of vulnerable configurations. In high-latitude systems, the response can start before the strongest interval arrives, because waiting for the grid to show stress is not the same as managing risk. The geography is uneven. Two regions can sit under the same geomagnetic storm, and experience different ground effects. The reason is conductivity. Some rocks conduct electricity better than others. Some shields of ancient crystalline bedrock are more resistive, meaning the induced electric field at the surface can be stronger. NOAA's US-Canada geoelectric field model was upgraded to estimate regional electric fields for power operators, with output updated every minute. NOAA notes that geoelectric field strength depends both on the space weather disturbance and on local Earth conductivity, and that higher resistivity areas can face higher grid impact risk. This is why northern North America matters. Canada and the northern United States sit under high geomagnetic latitudes, long transmission corridors, and geology that can amplify induced fields in certain regions. The upgraded NOAA model includes Canada and supports situational awareness for 37 major power transmission lines connecting the United States and Canada. That number matters because the grid is not a set of isolated islands, it is an interconnected machine. Power moves across borders between provinces and states through corridors that can become electrical collectors during geomagnetic disturbances. Europe faces the same physics in a different configuration. Scandinavia sits under the auroral zone, with long high-voltage lines crossing regions of varied ground conductivity. The United Kingdom monitors geomagnetic activity through observatories and models, because induced currents have been measured in power systems during past storms. Across northern Asia, Russia's high-latitude grid corridors occupy a vast region where the auroral oval can pass overhead during disturbed conditions. The storm is planetary, but the hazard map is drawn by latitude, geology, line length, and grid design. The most studied warning remains March 13th, 1989. During a severe geomagnetic storm, Quebec's power system lost voltage control after static VAR compensators tripped. Around 6 million people lost power for roughly 12 hours, according to the British Geological Survey's summary. That event was stronger than the current G3 forecast, but it remains the case that operators remember because it demonstrated how space weather can move through protective systems, voltage support, and transformers until a regional grid suddenly becomes unstable. The June 8th watch therefore sits in a narrower category, serious enough for operators, not extreme enough to justify public panic. The risk is not that every grid across 3 continents fails at once. The risk is that long, high-latitude networks experience currents they were not carrying yesterday, while transformers and protection systems must absorb a disturbance that arrives invisibly. The aurora may be the public signal. The real test is quieter. It is the movement of unwanted current through grounded metal, while engineers watch the sky as part of the grid. The night, the auroras moved south. The aurora begins in silence. No thunder crosses the sky when it forms, no pressure wave reaches the ground. The first visible sign, if the storm becomes strong enough and the clouds stay away, is a pale brightening toward the pole, low on the horizon, where the night seems to have a faint green edge. In places used to darkness, it can be mistaken for distant city light. In places far south of the usual auroral zone, it can look even stranger, a red wash above the tree line, too dim at first for the eye to trust, but clear enough for a camera to record. NOAA's forecast for June 8th places the strongest expected 3-hour KP value at 7 between 18:03 and 21 us UTC, the threshold for G3 or strong geomagnetic storm conditions. The same forecast shows G2 conditions continuing into the following 3-hour interval, then lingering G2 and G1 levels into the early part of June 9th. That is the operational window in which the auroral oval can expand far enough from the poles for observers outside the usual viewing belt to notice that something has changed above them. The sky does not glow because solar material burns in the atmosphere. It glows because charged particles, mainly electrons, are accelerated along Earth's magnetic field lines into the upper atmosphere. NOAA describes aurora as the result of electrons colliding with oxygen and nitrogen in the upper reaches of the atmosphere. Those atoms and molecules are pushed into higher energy states, then release light as they relax back down. The process is often compared to the way a neon light works, except the tube is planetary and the wiring is magnetic. The altitude matters. NOAA places aurora typically between 80 and 500 kilometers above Earth's surface. That means a display does not need to be directly overhead to be visible. A bright auroral curtain over southern Canada can be seen from the northern United States if the geometry is right. a red upper atmosphere glow can be visible from farther away because the emission occurs higher than the green light that usually forms closer to the lower edge of the auroral region. The horizon, not the map, becomes the first instrument. Under quiet conditions, the aurora forms two ovals centered approximately around the magnetic poles. These ovals are not fixed circles, they breathe with the magnetosphere. When solar wind energy enters Earth's magnetic environment, the ovals grow, shift, brighten, and move equatorward. Noe notes that during major geomagnetic storms, these ovals expand away from the poles, and during large events, aurora can be observed as far south as the United States, Europe, and Asia. That detail is why a storm forecast is also a visibility forecast. The larger the oval, the farther south the night can begin to glow. A G3 storm does not mean aurora will appear everywhere. It means the conditions have reached a category where aurora has historically been seen much farther from the poles than usual. NOAA's G3 scale states that aurora has been seen as low as Illinois and Oregon, roughly around 50 degrees geomagnetic latitude. The same scale ties G3 conditions to KP7. The implication is narrow but important. If the forecast verifies, the southern edge of realistic visibility can shift into regions where people do not normally plan their nights around the magnetosphere. The visual sequence often begins with shape before colour. In northern areas under the main oval, an arc can stretch from horizon to horizon. Later in the evening, especially near midnight, those arcs may twist, sway, and break into vertical rays. NOAA describes the peak of an auroral substorm as the moment when arcs can expand to fill the whole sky, moving quickly and becoming very bright. Farther south, the same event may appear less dramatic. A faint red dome, a green line low in the north, or an uneven glow that cameras capture more clearly than human eyes. The difference comes from both physics and biology. The eye is not equally sensitive to all colours in low light. Dim red aurora can be difficult to perceive directly, even when a long exposure image shows it clearly. Green aurora, produced mainly by oxygen around the lower auroral altitudes, is often easier to recognise. Red aurora, also produced by oxygen but generally higher up, can travel visually across greater distances because of its altitude, but it can appear faint to the naked eye. This is why reports from moderate storms often divide into two categories: people who saw the glow and people whose cameras saw it first. June adds another complication. In the high latitudes where aurora is most common, the nights are short. Twilight lingers late, especially across Canada, Alaska, Scandinavia, and northern Russia. NOAA notes that summer months at auroral latitudes can make observation difficult because the midnight sun prevents dark sky viewing. That does not weaken the storm, it weakens the observer's ability to see it. The magnetosphere may be active while the ground remains too bright for the evidence to become visible. Farther south, where nights are darker, the oval must expand more dramatically to bring the display into view. That creates an odd balance during June storms. Northern areas sit closer to the energy but fight daylight. Mid-latitude areas sit farther from the energy but may have darker skies. A strong enough storm can therefore produce better public visibility in regions that are not normally considered aurora country, especially where the northern horizon is open, rural, and free from low clouds. The June 6th CME creates the timing problem behind all of it. NOAA's discussion said the partial halo CME, first seen in LASCO C2 imagery at 14:01 UTC on June 6th, was anticipated to arrive around midday on June 8th. The forecast expected a disturbed solar wind environment by early to mid-UTC day, with enhanced magnetic field and faster solar wind continuing into June 9th. Those are the conditions needed to push the oval outward, but the scale of the display still depends on the magnetic orientation inside the incoming structure, especially where the BES turns south for long enough to feed the storm efficiently. That is why aurora reports become evidence. A sudden equatorward display is not just a beautiful side effect, it is a visible measurement of how much energy the magnetosphere has accepted. When the aurora moves south, it means the ring of particle precipitation has expanded. When it brightens rapidly or breaks into rays, it suggests a substorm release in the magnetotail. When red glow appears over areas that rarely see it, the storm is announcing its structure through light, before most people understand what the instruments have already shown. For grid operators, satellite controllers, radio users, and aviation planners, The aurora is not the hazard itself. It is the visible flag flying over a larger electrical system. The same energy that paints oxygen and nitrogen above the poles also disturbs the ionosphere, shifts currents over high latitudes, and changes the magnetic field measured at the ground. The sky becomes a display because the planet is conducting energy through its upper atmosphere. The power grid feels that same storm as current. The radio spectrum feels it as distortion. Navigation systems feel it as delay. If the June 8th forecast reaches G3 as expected, the public may remember the photographs first. The operational community will remember the graphs: KP, solar wind speed, density, BT, Boursys, and ground magnetic perturbation. The aurora is the part that makes the invisible visible. It is the storm writing across the atmosphere, briefly moving the polar night into places that normally never see it. The satellites in the storm layer. Above the weather, above the cloud tops, above the jet streams and blue atmosphere, the storm enters a region that looks empty from the ground. It is not empty. Low Earth orbit is crowded with working machines, discarded rocket bodies, fragments from older breakups, crewed spacecraft, scientific observatories, imaging satellites, broadband constellations, and military payloads whose positions are tracked quietly by radar and optical systems every day. This is where a geomagnetic storm becomes an orbital problem, not because the coronal mass ejection strikes satellites like debris. It does not. The danger is more indirect and harder to see. The storm changes the environment the satellites are moving through. It heats the upper atmosphere, it disturbs the ionosphere, it changes the density of the air at altitudes where engineers normally treat drag as small but never zero. NOAA defines low Earth orbit as the region below about 2,000 kilometers. The air there is thin beyond human experience, but it is not absent. The International Space Station and the Hubble Space Telescope both operate in low Earth orbit, and both require orbit management because atmospheric drag gradually lowers altitude. During active solar periods, NOAA notes that extrasolar energy heats the upper atmosphere, causing low-density layers to rise and denser layers from below to expand upward into satellite altitudes. The result is simple. Spacecraft fly into thicker air than expected, and drag increases. Under quiet solar conditions, low-orbit spacecraft can model this environment with enough confidence to plan maneuvers. During geomagnetic storms, the atmosphere stops behaving like a stable background. Heating can occur quickly. Density can increase over broad regions. Satellites lose a little more speed than expected on every pass. A small drag error becomes an orbit prediction error. An orbit prediction error becomes a tracking problem. A tracking problem becomes a collision avoidance problem when thousands of objects share similar altitudes. NOAA's geomagnetic storm scale makes the satellite warning explicit. At G2, corrective actions to satellite orientation may be required, and possible changes in drag can affect orbit predictions. At G3, surface charging may occur on satellite components, drag may increase on low Earth orbit satellites, and corrections may be needed for orientation problems. At G4, tracking problems and orientation corrections become more likely. At G5, the scale includes extensive surface charging, orientation problems, and uplink, downlink, and tracking difficulties. The forecast level matters because each step adds operational load before anything visibly fails. The most important modern example is not an ancient disaster. It happened on February 3, 2022, when SpaceX launched 49 Starlink satellites and later lost 38 of them after enhanced neutral density associated with a geomagnetic storm increased drag at their low deployment altitude. NOAA-linked researchers examined the event and found that the storm environment made the satellite's early orbit far more hostile than expected. The event was not a Carrington-level catastrophe. It was a modest storm in the wrong orbital situation, at the wrong altitude, during the wrong phase of deployment. That detail matters. Satellites do not all face the same risk. A spacecraft already established in a higher, stable orbit may only need minor planning changes. A newly launched satellite still climbing from a low parking orbit can be exposed. At lower altitude, the atmosphere is denser. If drag increases before the spacecraft raises its orbit, it may lose altitude faster than its propulsion system can recover. In that narrow window after launch, a storm that looks moderate on a public scale can become expensive in orbit. The June 8th G3 watch sits directly inside that operational category. it does not imply a guaranteed satellite loss. It does imply that operators in low Earth orbit will be watching thermospheric density, drag forecasts, onboard attitude, and tracking updates more closely than usual. Broadband constellations, Earth observation satellites, CubeSats, and newly deployed spacecraft all depend on accurate orbit prediction. When the atmosphere expands, the catalogue changes. Objects are not where yesterday's model expected them to be. The storm layer does not stop at drag. Spacecraft also have to survive charging. In disturbed geomagnetic conditions, energetic particles can accumulate on satellite surfaces or penetrate materials and deposit charge internally. If different parts of a spacecraft build up different electrical potentials, a discharge can occur. A discharge does not need to be large to matter. Inside a satellite, a brief electrical event can upset electronics, confuse sensors, degrade components, or trigger protective modes. At G3, NOAA states that surface charging may occur on satellite components. At higher levels, the language becomes more serious. Attitude control becomes another quiet vulnerability. A satellite needs to know where it is pointing. Earth observation satellites must aim instruments at the surface. Communication satellites must point antennas correctly. Solar panels must face the sun. Many spacecraft use star trackers, sun sensors, magnetometers, gyroscopes, reaction wheels, and onboard software to maintain orientation. During geomagnetic disturbances, increased drag can add torque. Particle effects can interfere with electronics. Magnetic field disturbances can complicate systems that use Earth's field as part of attitude knowledge. The spacecraft is still in orbit, but the environment around it has become noisier. Communication is tied to the ionosphere beneath the satellites. Signals passing between satellites and receivers on Earth travel through ionized layers that are altered during geomagnetic storms. NOAA describes geomagnetic storms as disturbances that can affect satellite navigation and radio systems, and its G3 scale includes intermittent satellite navigation and low-frequency radio navigation problems. For ordinary users, that may look like degraded GPS accuracy, unstable correction services, or brief positioning errors rather than a complete outage. For aviation, maritime operations, surveying, agriculture, drilling, emergency response, and military navigation, brief errors can matter. The more crowded low Earth orbit becomes, the more these small disturbances matter. Each satellite has its own flight rules, maneuver limits, fuel margins, communication windows, and ground control schedule. During a storm, operators may delay launches, postpone orbit-raising burns, adjust attitudes to reduce drag, increase tracking cadence, or hold spacecraft in safe modes. Space traffic systems must account for the fact that many objects are being displaced by the same atmospheric expansion at once. The storm does not need to destroy satellites to complicate the map. The public sees aurora. Operators see uncertainty expanding through orbital predictions. The same energy that sends light into the polar atmosphere also lifts the atmosphere upward into the paths of spacecraft. It turns a region people imagine as a vacuum into a moving, breathing boundary. The June 6th CME is therefore not only a ground grid event or a sky event, it is a test of the satellite layer that modern life increasingly depends on. Navigation, broadband, weather forecasting, timing, remote sensing, and defense systems moving silently through an atmosphere that the sun can still reach. The navigation error nobody notices. A tractor can lose the sky before the driver knows anything is wrong. The field may still be flat, the row still visible, the receiver still locked to satellites overhead. On the display, a guidance line that should hold steady begins to drift. The machine does not stop. It becomes less certain of where it is. In aviation, the same uncertainty can appear as degraded approach availability. At sea, it can enter a chart plotter. In a survey cruise receiver, it can stretch a fixed point into a moving answer. GPS works by turning time into distance. Each satellite carries an atomic clock and broadcasts a signal containing its position and the precise time of transmission. A receiver compares that time with the moment the signal arrived. The difference gives a range. With ranges from several satellites, the receiver solves for position and clock error. It happens continuously, but every solution depends on one hidden assumption. The signal's path through the atmosphere can be modelled well enough. The ionosphere is where that assumption becomes vulnerable. It begins roughly 60 kilometers above Earth and extends hundreds of kilometers upward, a region where solar radiation separates electrons from atoms and molecules. NOAA describes it as an electrically charged layer that changes with sunlight, solar flares, solar wind, and geomagnetic storms. During ordinary days, those changes follow patterns. During a storm, the patterns can sharpen, fragment, and move faster than a navigation model expects. GPS signals must cross that charged region before they reach the ground. Free electrons in the ionosphere alter the speed and path of radio waves. The measure that matters is total electron content, or TEC, the height-integrated number of electrons along the signal path. NOAA's space weather guidance states that geomagnetic storms enhance the ionosphere and increase TEC, and that GPS systems cannot always model that dynamic enhancement correctly, allowing position errors to enter the calculation. The effect usually concentrates at high latitudes, but major storms can extend large TEC disturbances into middle latitudes. This is not the kind of failure most people imagine. The phone may still show a blue dot, the aircraft may still receive satellites, the ship may still plot a course. The problem is accuracy, reliability, and integrity. A navigation system can be wrong by a little and still look functional. That is why the error can be more operationally interesting than a complete outage. A blank screen announces itself. A confident but degraded position has to be detected. The June 8th watch matters because NOAA's scale links G3 conditions to intermittent satellite navigation problems, including degraded low-frequency radio navigation and possible GPS issues. The same G3 category also includes increased drag on low Earth orbit satellites and surface charging on spacecraft components. Those are different symptoms of the same larger disturbance. Energy entering the magnetosphere, altering the ionosphere and upper atmosphere, then pushing errors into systems that depend on predictable conditions. The Federal Aviation Administration frames the aviation side directly. Its space weather program notes that GPS and GNSS can be affected during solar events that disturb the ionosphere because navigation signals pass through ionized plasma before reaching receivers. That plasma bends the signal, and during solar events the accuracy of those signals can degrade, impairing aviation navigation tools. The setting is concrete, an aircraft descending through clouds toward a runway, trusting a satellite-based system to define where the runway environment begins. Modern aviation does not rely on raw GPS alone. It uses ground procedures, onboard receivers, barometric instruments, inertial references, radar, air traffic control, and satellite-based augmentation where available. A G3 storm does not make aircraft unsafe by itself. It can reduce availability or margins. A precision approach may become unavailable before the pilot notices anything dramatic. A system designed to protect integrity may remove service rather than risk giving a bad solution. That is not failure. It is the system refusing to pretend certainty exists. Farming shows the same physics in a quieter landscape. Precision agriculture depends on GNSS receivers to guide tractors, planters, sprayers, and harvesters along paths measured in centimeters rather than meters. Many systems use real-time corrections from ground networks or satellites. When ionospheric conditions become disturbed, corrections may arrive late, lose lock, or no longer represent the local sky accurately. During the severe May 10th and 11th, 2024 geomagnetic storm, GPS users reported positioning errors and outages, with farmers in the central United States specifically reporting difficulty getting fixes for tractors and equipment. Surveying and construction are even less forgiving. A boundary point, bridge alignment, pipeline corridor, or machine control grade depends on repeatable positioning. A few centimeters can matter. High-precision GNSS receivers use carrier phase measurements and correction streams to reach that accuracy, but the ionosphere can introduce rapid phase changes and scintillation. Scintillation means the signal fluctuates in amplitude or phase as it passes through irregular plasma. A receiver may lose lock, take longer to resolve ambiguities, or report lower confidence. The disturbance is above the atmosphere, but the delay appears in a surveyor's tripod on the ground. Maritime navigation adds another layer. On open water, a ship's bridge integrates GNSS with radar, charts, AIS, inertial references, and human watchkeeping. A degraded satellite position may not endanger a vessel in open ocean, but near harbours, offshore platforms, narrow channels, or poor visibility, errors reduce margins. The same is true for emergency response, search and rescue, utility crews, mining operations, timing networks, and financial systems that use GNSS-derived time. GPS is not only a map tool, it is also a clock distributed from orbit. That clock function is easy to overlook. Telecommunications networks, power grid phaser measurement units, data centers, financial exchanges and broadcast systems use satellite timing because GPS satellites carry extremely stable clocks. A geomagnetic storm that disturbs signal propagation can affect more than position. It can challenge timing receivers, especially where antennas have limited sky view, backup oscillators are weak, or systems depend on a single source. The public thinks of GPS as directions. Infrastructure uses it as time. The error nobody notices is not invisible because it is small. It is invisible because it hides inside systems that normally correct themselves. Receivers reject bad satellites. Augmentation systems warn users when integrity cannot be maintained. Operators fall back to alternate procedures. Pilots revert to other navigation aids. Survey crews wait for the sky to settle. Farmers pause work or switch guidance modes. A geomagnetic storm forecast is therefore also a navigation forecast. The June 6th eruption, the June 8th G3 watch, and the expected disturbed conditions into June 9th describe more than aurora and grid current. They describe a planet whose upper atmosphere may become a moving lens between satellites and receivers. The signal still leaves orbit at the speed of light. It still reaches the antenna. But for a few hours, the space between the two may stop behaving like the model promised. The radio blackout on the polar route. A polar flight crosses a part of the world where silence has weight. Below the aircraft, the map becomes ice, ocean, darkness, and a few distant weather stations scattered across impossible distances. There are no cities close enough to form a radio horizon. No chain of airports follows the route like lights on a highway. Between North America and Asia, or across the far northern reaches of the Atlantic, aircraft move through airspace where communication must stretch far beyond ordinary line of sight. That is why high-frequency radio still matters. Very high-frequency radio, the familiar aircraft band used closer to populated airspace, travels mostly in straight lines. It works well when ground stations are nearby. HF radio behaves differently. It can bend back toward Earth after interacting with the ionosphere, allowing messages to cross oceans, polar regions, and remote continents. The system is old, but it survives because geography still requires it. Space weather enters this system through the layer that makes HF useful in the first place. The ionosphere is not a passive mirror. It is a region of charged particles shaped by sunlight, geomagnetic activity, solar flares, energetic particles, and night. When it is stable, radio operators choose frequencies that will return cleanly from the sky. When it is disturbed, the same layer that carried the signal can absorb it, scatter it, shift it, or refuse to return it at all. The Federal Aviation Administration describes the aviation problem directly. Space weather can cause communication frequency degradation and blackouts, and solar radiation storms in particular can make HF communications inoperable during polar flights. The FAA also notes that polar and oceanic regions are most susceptible because long-range communication is required there. In that sentence, the operational risk is already visible. The aircraft may be functioning normally, the engines may be stable, the route may be legal, but the communication path can degrade above the horizon where no crew member can see it. There are three related hazards that are often blended together in public reporting, but they are not the same. A solar flare can cause a radio blackout on the sunlit side of Earth. A solar radiation storm can drive energetic protons into polar regions and degrade HF propagation through the polar caps. A geomagnetic storm can disturb ionospheric structure, especially at high latitudes, and make HF propagation intermittent. The June 8th watch is a geomagnetic storm watch. That distinction matters because it points to a different mechanism than a flare-driven daylight blackout. NOAA's scale separates these categories. For G3 geomagnetic storms, the expected other systems impacts include intermittent satellite navigation and low-frequency radio navigation problems, and HF radio may be intermittent. For stronger G4 and G5 geomagnetic storms, HF propagation can become sporadic or impossible in many areas for longer periods. The current forecast category does not imply a guaranteed global communications failure. It does imply that high-latitude radio circuits may become unreliable enough to force operational attention. A separate NOAA category, the radio blackout scale, is tied to solar flares. At R1, HF radio on the sunlit side may see weak or minor degradation with occasional loss of contact. At R3, NOAA describes a wide area HF blackout on the sunlit side lasting about an hour. At R5, complete HF blackout can occur across the sunlit side for hours, producing no HF radio contact with mariners and en route aviators in that sector. This is why the timing of a flare matters. The affected half of Earth is the side facing the sun when the X-rays arrive. Polar aviation has an additional vulnerability. During solar radiation storms, energetic particles are guided by Earth's magnetic field into high-latitude regions. NOAA's solar radiation scale states that at S3, degraded HF radio propagation through the polar regions and navigation position errors are likely. At S4, HF blackout through the polar regions and increased navigation errors over several days are likely. At S5, complete HF blackout through the polar regions becomes possible. A CME-driven geomagnetic watch is therefore only one part of the aviation space weather picture. The polar route is exposed because several solar hazards converge there. Inside an aircraft cockpit, this does not appear as a science diagram. It appears as a call that does not go through. A crew tries a primary HF frequency, then a secondary one. The signal carries noise, fading, or nothing. Controllers may still see the aircraft through satellite surveillance or procedural reporting systems, depending on the region and equipment. Satellite communications may be available as a backup, but the operational requirement remains simple. An aircraft crossing remote airspace must be able to communicate reliably with air traffic control and company dispatch. The FAA notes that procedures already exist to mitigate these impacts, including shifting to less affected higher HF frequencies. That sounds modest until the setting is remembered. A dispatcher, a controller, and a flight crew are not solving an abstract radio problem. They are managing separation, route changes, medical contingencies, fuel decisions, turbulence avoidance, diversion options, and weather. While one of the long-range communication layers becomes unstable, the mitigation is routine because the hazard is known. It is still a workload increase. Physics is highly selective. A passenger streaming a movie over onboard Wi-Fi may not notice anything. A city radio station may be untouched. An aircraft over land with VHF coverage may continue normally. Meanwhile, a high-latitude HF circuit can degrade because the ionosphere above the polar cap has changed enough to alter propagation. Space weather does not hit every technology equally. It finds the systems that depend on the part of the atmosphere being disturbed. The June 6th eruption adds timing to the concern. NOAA's discussion placed CME arrival around midday UTC on June 8th, with disturbed solar wind expected through June 9th. The strongest geomagnetic interval in the 3-day forecast reaches KP7, the G3 threshold, during the June 8th UTC evening window. That places the radio risk inside a moving global clock, where the aircraft is, whether its route crosses high geomagnetic latitudes, what side of Earth is sunlit, and whether the ionosphere is storming locally when the communication attempt happens. A radio blackout is not always dramatic. Sometimes it is a few minutes of fading. Sometimes a frequency that worked an hour earlier becomes unusable. Sometimes a route can continue with alternate communication. Sometimes dispatchers and operators choose to avoid the exposure altogether by flying farther south, accepting extra fuel burn and time in exchange for more reliable communications and lower radiation concerns. The decision depends on the storm category, available equipment, company procedures, and the forecast confidence. The deeper lesson is that modern aviation still negotiates with the upper atmosphere. Aircraft may be digital, satellite-linked, precisely routed and globally tracked, but the polar sky remains a difficult communications environment when the sun becomes active. The same storm that may paint auroras and disturb power lines can also make a radio wave vanish between an antenna and the ionosphere. Nothing falls from the sky. No visible wall blocks the route. The signal simply reaches upward and finds that the layer it trusted has changed. The radiation corridor above the clouds. At cruising altitude, the sky's thinner than it appears from a passenger window. The cabin is pressurized, the coffee is warm, the route map is calm, and the aircraft feels separated from space by the same ordinary blue that covers the ground below. But outside the aluminum skin, at 32,000 to 40,000 feet, the atmosphere has already lost much of its shielding power. The airplane is still inside Earth's weather system. It is also closer to a radiation environment most people never consider. Radiation exposure in aviation has two main sources. The first is galactic cosmic rays, high-energy particles that usually come from outside the solar system, often associated with violent astrophysical processes such as supernova remnants. The second is solar energetic particles, or SEPs, charged particles accelerated by eruptions on the Sun. The Federal Aviation Administration identifies both as radiation sources affecting aviation and notes that they can be harmful to humans and aircraft hardware. The difficulty is not whether the particles exist. The difficulty is measuring and modelling their dose at flight altitude during a changing storm. Altitude changes the calculation. At sea level, the atmosphere is a thick shield. Particles from space collide with air molecules high above the ground, producing cascades of secondary particles that are mostly absorbed before they reach people on the surface. An aircraft crossing the upper troposphere has less atmosphere above it. The shield is still there, but thinner. Each kilometre gained upward reduces the mass of air protecting the cabin. That is why frequent flyers and aircrew receive more cosmic radiation exposure than people who rarely leave the ground, even during quiet space weather. Latitude adds the second filter. Earth's magnetic field deflects many charged particles, but it does not protect every region equally. Near the equator, the field lines create a stronger magnetic barrier against incoming charged particles. Near the poles, the geometry becomes more open. Particles guided along magnetic field lines can penetrate deeper into the atmosphere at high latitudes. A route passing near the Arctic is therefore not the same radiation environment as a route crossing the tropics at the same altitude. NOAA's description of solar radiation storms begins at the Sun. A large-scale magnetic eruption, often associated with a coronal mass ejection and a solar flare, can accelerate protons to a large fraction of the speed of light. At those speeds, NOAA notes that protons can cross the 150 million kilometers from the Sun to Earth in tens of minutes or less. That timing matters. A CME may take days to arrive. The fastest solar energetic particles can arrive long before the magnetic cloud itself. Once those particles reach Earth, they do not spread evenly across the globe. NOAA explains that fast-moving protons penetrate the magnetosphere and are guided down magnetic field lines into the atmosphere near the North and South poles. There, they can increase radiation exposure at flight altitudes and also create ionization low in the ionosphere, absorbing high-frequency radio waves. This is the same polar geography that complicates communication. The radiation corridor and the radio corridor overlap because both are shaped by magnetic access to the polar atmosphere. A geomagnetic storm watch is not automatically a solar radiation storm warning. That distinction is critical. The June 8th watch describes expected geomagnetic storming from the arrival of the June 6th CME. Solar radiation storms are tracked on a separate NOAA scale, labelled S1 through S5, based on energetic proton flux, measured by Gauss satellites in geosynchronous orbit. NOAA defines the start of a solar radiation storm when protons at energies greater than or equal to 10 megaelectron-volts reach or exceed 10 proton flux units. The end is the last time that flux remains at or above that threshold. The scale shows why aviation operators take the category seriously. At S2, NOAA says passengers and crew in high-flying aircraft at high latitudes may be exposed to elevated radiation risk. At S3, radiation hazard avoidance is recommended for astronauts on spacewalks, and passengers and crew in high-flying aircraft at high latitudes may be exposed to radiation risk. At S4 and S5, the language becomes more severe, including unavoidable radiation hazard for astronauts outside spacecraft and risk exposure for high-latitude, high-flying aircraft. The same scale ties stronger events to polar HF blackout and navigation errors. Inside an airline operations centre, this is not an abstract health discussion. A dispatcher looking at a polar route must weigh winds, fuel, alternate airports, communications, navigation availability, radiation exposure and crew duty time. A shorter Great Circle route over the high Arctic may save fuel and time on an ordinary day. During a significant solar radiation event, that same route may carry higher exposure and weaker communication reliability. Flying farther south may cost fuel but reduce space weather risk. The FAA's Space Weather Aviation Program states that radiation hazards are difficult to determine because the evidence base includes uncertainty. with many studies relying on models rather than direct observations and measurements. The agency also notes that the lack of radiation observations at cruise altitudes contributes to that uncertainty. That sentence is less dramatic than a warning, but more important. It means the aviation system is operating with models, procedures, and limited measurements in an environment that can change quickly above the aircraft. Aircrew occupy a special category because exposure accumulates. A passenger may take one long polar flight and never think about the subject again. Pilots and flight attendants repeat the route for years. Regulators treat that accumulated occupational exposure differently from the exposure of a single traveller. FAA advisory circular material on in-flight radiation exposure provides background for operators, and the FAA states that air carriers are responsible for developing safety and measurement procedures to inform and protect crew members from in-flight ionizing radiation exposure. The passenger cabin hides nearly all of this. Nothing in the aisle changes colour when particles arrive. No warning light appears above seat 32. The aircraft does not shake because protons entered the polar atmosphere. A storm can affect radiation dose while remaining completely invisible to everyone on board. The evidence belongs to satellites, proton monitors, radiation models, route planning systems, and dispatch decisions made before passengers hear the boarding announcement. That is why the high-altitude corridor matters. Space weather does not need to break an aircraft to change aviation. It can alter the invisible operating environment around the route. It can force operators to ask whether the fastest track is still the best track, whether HF backup remains dependable, whether navigation integrity is strong enough, and whether accumulated crew exposure should be reduced. The sun's disturbance may begin as magnetic stress above an active region. By the time it reaches aviation, it has become a question written across altitude, latitude, and time, the forecast that can still fail. Inside the forecast room, certainty is not the working condition. The monitors may show solar images, model tracks, magnetic field plots, proton flux, X-ray curves, and planetary K-index forecasts arranged in neat panels, but the system being watched is not neat. A coronal mass ejection is not a train on a fixed rail. It is a magnetic structure moving through a moving medium, expanding as it travels, colliding with old streams, crossing interplanetary space with details that cannot be fully measured from Earth. The June 6th event gave forecasters enough to act. NOAA's forecast discussion identified the source as an M1.8 flare from region 4461 at 1401 UTC, accompanied by a 10.7 centimeter radio burst, an 11-degree-long filament eruption, and a Type 2 radio sweep with an estimated speed of 838 km per second. LASCO C2 coronagraph imagery showed the partial halo CME at the same UTC minute, and S2PC expected arrival around midday on June 8th. That is a forecast built from evidence, but not a guarantee. A coronagraph shows outward motion, not the entire magnetic anatomy. It can reveal a bright front, an expanding halo, a symmetry, and speed projected across the plane of the sky. It cannot fully show whether the most geo-effective part of the cloud will strike Earth directly, pass north or south, or graze the magnetosphere with only its flank. A wide eruption can appear threatening and then underperform. A less dramatic structure can arrive with a southward magnetic field and produce stronger effects than its imagery suggested. The problem is not poor forecasting. The problem is geometry. Arrival time is the first uncertainty. A CME leaving the Sun at hundreds of kilometers per second must cross roughly 150 million kilometers before Earth can measure it directly. During that crossing, the eruption moves through the solar wind, which is itself variable. Faster solar wind can push from behind. Slower wind ahead can compress the front. Coronal hole streams can alter the path. Older disturbances can change the density of the medium. A forecast arrival window may be off by several hours, and those hours matter when operators are staffing control rooms, adjusting maintenance schedules, or preparing satellite maneuvers. The second uncertainty is worse because it decides intensity. It is the magnetic orientation inside the CME. The parameter everyone waits for is BEAS, the north-south component of the interplanetary magnetic field. Southward BEAS couples efficiently with Earth's dayside magnetic field. Northward BEAS resists that coupling. The same cloud can produce very different geomagnetic outcomes depending on which direction that field points when it reaches Earth. The forecast can know the storm is coming, and still not know whether the key inside the cloud is turned the right way. This is why L1 matters. DSCOVR, positioned near the first Lagrange point about 1 million miles from Earth, monitors the solar wind before it reaches the planet. NASA describes DSCOVR as a space weather station, providing alerts and forecasts for geomagnetic storms that could disrupt power grids, satellites, telecommunications, aviation, and GPS. Its position allows forecasters roughly 15 to 60 minutes of warning before solar storms arrive at Earth. That is not much time, but it is the difference between watching a model and measuring the actual incoming plasma. When the shock reaches L1, the graphs change quickly. Solar wind density may jump, speed can rise, temperature can spike. The total magnetic field, often labelled beat, can strengthen. Then Bayer begins to matter minute by minute. If BES turns strongly south and stays there, the magnetosphere opens more efficiently to solar wind energy. If it fluctuates or remains mostly north, the storm may arrive with force but couple weakly. The public sees a single forecast category. Operators see a time series with consequences. NOAA's 3-day forecast issued on June 7th placed the greatest expected 3-hour KP at 7, the threshold for G3 conditions, on June 8th. The same forecast showed G1 and G2 periods leading into that window, followed by G2 and G1 conditions into June 9th. It also assigned a 25% chance of S1 or greater solar radiation, storming on June 8th, and a 55% chance of R1 to R2 radio blackouts across June 7th through June 9th, with a 10% chance of R3 or greater events. The categories are separate, but the operational calendar is the same. That is the complexity hidden behind a simple phrase like solar event. Geomagnetic storming, solar radiation storms, and radio blackouts are not one hazard with one switch. NOAA's scales separate them because their physical causes and impacts differ. Geomagnetic storms come from solar wind energy entering Earth's magnetosphere. Solar radiation storms involve energetic particles, especially protons. Radio blackouts are caused by enhanced X-ray emission from solar flares affecting the sunlit ionosphere. They can overlap, but they do not have to peak together. Forecast failure can happen in two directions. The event can fail upward, becoming stronger than expected if the CME arrives faster, denser, more magnetically intense, or more southward than modelled. It can also fail downward, arriving late, weak, glancing, or with a northward field. Both outcomes are normal in space weather. The important distinction is that an underperforming storm does not mean the watch was meaningless. It means the uncertainty broke in a favourable direction. There is also the problem of public interpretation. A G3 watch sounds precise. It is not a promise that every place under high latitude will see impacts. It is not a promise that every satellite operator will experience trouble, or every power grid will report abnormal currents. It is a probabilistic operational warning built around the best available evidence. NOAA's G3 category includes possible voltage corrections, false alarms on some protection devices, satellite surface charging, increased drag on low Earth orbit spacecraft, intermittent satellite navigation problems, intermittent HF radio, and aurora seen as low as Illinois and Oregon. The word possible is carrying real weight. By the final hour before arrival, the forecast becomes less like prediction and more like tracking weather radar before a landfalling storm. L1 does not reveal the CME days ahead. It gives the last upstream measurement. From that point, the disturbance is already close. Power grid operators can confirm whether currents are likely to rise. Satellite controllers can update drag assumptions. Radio users can watch absorption and propagation products. Aurora forecasters can sharpen the visibility map. The long wait collapses into a few decisive data points. The most dangerous mistake would be to treat uncertainty as ignorance. Space weather forecasting has improved because spacecraft now stand upstream of Earth. Coronagraphs watch the solar corona, and models trace the solar wind between the Sun and the planet. But the Sun still keeps part of the answer hidden until the storm is almost here. That is the final vulnerability in the next 72 hours. Not that no one is watching, but that the most important measurement may arrive only shortly before the effects begin. The planet under the same magnetic weather. No border exists in the magnetosphere. The disturbance does not stop above customs lines, coastlines, military airspace, shipping lanes, or power market territories. It arrives as a planetary condition, wrapped around Earth by magnetic geometry. then breaks into local consequences only when it touches human systems. One solar eruption can become a voltage problem in Quebec, a tracking problem in low Earth orbit, a navigation error over a farm field, a radio fade on a polar route, and a red glow above a town that has no reason to expect aurora. The June 6th eruption entered the forecast as an M-class flare, a filament eruption, a radio burst, and a partial halo CME. NOAA's forecast discussion placed the source at region 4461, with the CME first seen in LASCO C2 imagery at 1401 UTC and expected to reach Earth around midday on June 8th. The 3-day forecast placed the strongest expected geomagnetic interval at KP7, the G3 threshold, during the evening UTC hours of June 8th, with G1 and G2 storming around it and lingering into June 9th. Those are operational numbers, but their meaning is not contained inside one scale. The scale is only the doorway. NOAA's G3 category does not describe a single effect. It describes a family of possible impacts: voltage corrections in power systems, false alarms on some protection devices, surface charging on spacecraft components, increased drag on low Earth orbit satellites, possible orientation corrections, intermittent satellite navigation problems, intermittent HF radio, and aurora visible far south of its usual range. A storm category is therefore not a label for one disaster. It is a map of stress points across a technological civilization. The first stress point is metal stretched across distance. Transmission lines were built to move electrical power, not to collect electric fields induced by a changing magnetosphere. During a geomagnetic storm, currents high above Earth disturb the magnetic field measured at the ground. That changing field induces electric fields across the surface, and long conductors become pathways. The current is slow, almost direct in character, and it enters through transformer grounding points. It does not need to destroy equipment to matter, it only needs to push the system away from the state engineers expected. A second stress point moves overhead every 90 minutes. Low Earth orbit is often imagined as a clean vacuum, but NOAA notes that solar and geomagnetic activity can heat the upper atmosphere, expand denser layers upward, and increase drag on satellites. The effect is not cinematic. A spacecraft simply loses a little more speed. Its predicted position becomes less exact. If thousands of objects are being tracked, and many are affected together, uncertainty spreads through the catalogue. The storm becomes a traffic problem in a region where there are no lanes. A third stress point is timing. Navigation satellites are clocks in orbit, and modern infrastructure depends on those clocks with a quietness that makes the dependency easy to miss. A receiver calculates position by measuring how long signals took to arrive, but the signals pass through the ionosphere, and the ionosphere is one of the places geomagnetic storms disturb most efficiently. When electron content changes rapidly, the path delay changes with it. The result may not be a blank screen. It may be an answer that is slightly wrong, late, unstable, or rejected by an integrity system that refuses to trust the sky. A fourth stress point is communication. High-frequency radio uses the ionosphere as part of the circuit. That is why it can cross oceans and polar regions. It is also why space weather can degrade it. When the ionosphere absorbs, scatters, or distorts the signal, a route that looked routine on a map can become less routine in the cockpit. Aviation has procedures for this. Operators can shift frequencies, use satellite communications, alter routing, or plan around polar exposure. But a mitigation is not the absence of risk. It is evidence that the risk has already been built into the system. Above the clouds, another calculation belongs to radiation. A geomagnetic storm is separate from a solar radiation storm, and NOAA tracks them on different scales. But the same active solar environment can raise multiple questions at once. Solar energetic particles, when present, are guided into high-latitude regions by Earth's magnetic field. Aircrew on polar routes, astronauts outside spacecraft, and satellite electronics are not exposed in the same way as people at sea level. The atmosphere is a shield, but at cruising altitude it is thinner, and near the poles the magnetic shield has openings that the equator does not. All of these systems share one uncomfortable feature. Their most important vulnerabilities are often invisible to the public. A transformer does not need to smoke for the grid to be stressed. A satellite does not need to fall for operators to lose confidence in its predicted orbit. A GPS receiver does not need to shut down for positioning to degrade. A radio does not need permanent silence to create operational friction. An aurora may be the most visible signature of the storm, but visibility is not the same as consequence. That is why the last measurement before impact matters so much. Coronagraphs can show the CME leaving the Sun. Forecast models can estimate arrival. Watchers can define expected categories. But the magnetic field inside the cloud, especially BESS, may not be known well until the structure reaches spacecraft upstream of Earth. A northward field can blunt the storm. A sustained southward field can unlock it. The difference between an impressive sky event and a serious operational event can be hidden inside a direction, measured only shortly before arrival. The phrase 3 continents can make the event sound like a single wave hitting everything equally. It is more precise to say the same magnetic weather can place North America, Europe, and Northern Asia under related exposure, while the actual impacts vary by latitude, geology, infrastructure, orbital altitude, route planning, and timing. A high-latitude grid in resistive ground is not the same as a low-latitude urban network. A newly deployed satellite is not the same as a mature spacecraft in a higher orbit. A polar flight is not the same as a domestic route under dense ground communication coverage. That is the real shape of the event, not a guaranteed collapse, not a harmless light show. A coupled planetary disturbance moving through systems that were built on the assumption that near-Earth space is usually stable enough to model. For most people, the memory may be photographs of red and green light. For operators, it will be a set of traces: KP, BT, BZs, solar wind speed, proton flux, TIC maps, transformer neutral currents, orbit residuals, and radio absorption products. The Sun does not need to touch Earth to test it. It only needs to change the magnetic weather around the planet, then wait as every dependent system reveals how much of modern life has been quietly built inside that weather. The storm may pass with nothing more than auroras, scattered signal problems, and a few tense hours inside control rooms. Or it may expose the parts of modern life that depend on a quiet sun more than we realize. The grid, the satellites, the aircraft, the radio bands, the navigation systems, all of them are tied to the same magnetic weather above the planet. If you want to follow what happens when the next solar disturbance leaves the Sun, subscribe, stay with the data, and watch the sky carefully. The next one may already be forming.